A vast darkness once filled the cosmos between its fiery birth and the first stars. This was the universe's forgotten Middle Age, a mysterious epoch that crafted the very fabric of our reality. By the end of this journey, you will understand how this hidden era built the foundation for every galaxy, star, and planet we see today. How did a void of nothingness give rise to everything? What cosmic forces were at work in the shadows? What does it feel like to uncover a chapter of history written before time itself had meaning? The universe began not with a whisper, but with a roar of pure energy. In the immediate aftermath of the Big Bang, everything that existed was compressed into a searing, opaque fog, a plasma so hot that not even light could travel freely through it. For hundreds of thousands of years, this cosmic soup of particles and radiation expanded and cooled relentlessly. Then, a profound transformation occurred. Electrons slowed enough to be captured by protons, forming the first atoms, mostly hydrogen. In that moment, the fog cleared, the universe became transparent, and for the first time, darkness fell. This was not the darkness of empty space as we know it, but a profound and total cosmic night. There were no stars, no galaxies, not a single point of light to pierce the endless void. The cosmos was a vast, silent sea of neutral hydrogen gas, a blank canvas awaiting its first masterpiece. Cosmologists see this era as the ultimate foundation. Every great structure needs a stable base, and this dark age provided exactly that. The slight ripples in density left over from the Big Bang were frozen in place, tiny seeds of potential gravity waiting for their moment to grow. How could such a uniform, featureless expanse give rise to the brilliant complexity we see today? The answer lies in the quiet, relentless pull of gravity, which began its slow, patient work in the dark, gathering those tiny seeds into the first structures that would eventually ignite and end the long cosmic night. That profound cosmic night could not last forever. Deep within the darkness, gravity was at work, patiently pulling the densest patches of hydrogen gas into the first structures. Then a spark. In pockets of collapsing gas, the very first stars ignited, and the universe awoke from its slumber. This was the dawn of the epoch of reionization, a cosmic revolution that would fundamentally reshape the cosmos. These first stars were not like our sun. They were behemoths, hundreds of times more massive, burning ferociously hot and brilliant. They flooded the universe with its first true light, a torrent of ultraviolet radiation. This intense energy began to tear apart the neutral hydrogen atoms that filled the cosmos, stripping electrons away in a process we call reionization. Think of it as a great thaw where a frozen, opaque sea of gas was slowly, over hundreds of millions of years, transformed back into a transparent plasma. This was the moment the universe became the clear, vast space we recognize today. How can we possibly witness such an ancient event? Our most powerful telescopes, like Hubble and the James Webb Space Telescope, act as time machines. They do not see the starlight itself, but they detect the faint afterglow of this reionization process. They collect ancient photons that have traveled for over 13 billion years, carrying the imprint of that final clearing. It is an immense challenge, like trying to read a faded letter from the edge of time. One of our best clues comes from quasars, the intensely bright cores of early galaxies. These objects act as cosmic lighthouses. Their light, as it journeys to us, passes through the leftover hydrogen from this era. By studying how that light is absorbed, we can map the final patches of neutral gas, charting the progress of reionization across the cosmos. Can you envision those first brilliant sparks scattered throughout an infinite darkness? They were more than just light. they were the architects of the future. Their radiation carved out vast transparent regions, and their violent deaths in supernova explosions seeded the cosmos with the first heavy elements, the very stuff of planets and life. These initial acts of creation set the stage for everything to come, forcing us to ask, how exactly did those first structures gather enough material to ignite in the first place? But what was the force that guided this gas, that sculpted those first structures from the void? The answer lies in something we cannot see. An invisible architect was at work, a substance known as dark matter. While the Dark Ages were filled with neutral hydrogen gas, this ordinary, visible matter was not the main character in the story of cosmic structure. It was outnumbered 5-1 by dark matter, a mysterious substance that does not absorb, reflect, or emit light. Its presence is felt only through its immense gravitational pull. During the universe's Middle Age, dark matter formed a vast, invisible scaffolding. Its gravity created the first wells, the first concentrations of mass, and the neutral hydrogen gas simply flowed into these gravitational potholes. Without this unseen framework, the gas would have been too diffuse, its gravity too weak, to ever collapse into the dense clouds that birthed the first stars and galaxies. One leading cosmologist put it this way: dark matter provided the gravitational muscle, while ordinary matter simply went along for the ride. We have compelling evidence for this hidden cosmic infrastructure. The faint patterns in the cosmic microwave background, the afterglow of the Big Bang, show us the precise distribution of matter in the infant universe. Those patterns perfectly match a model where dark matter dominates. Later, when we look at how galaxies spin, we see another clue. The stars on the outer edges of galaxies rotate just as fast as those near the center. According to the laws of gravity, this should not happen unless there is a huge amount of invisible mass, a dark matter halo, surrounding the visible galaxy and holding it all together. Supercomputer simulations bring this process to life. They show dark matter coalescing first into a delicate cosmic web, with vast filaments connecting at dense nodes. At these intersections, dark matter halos form, and it is within these halos that the first proto-galaxies begin to take shape, nurtured by the relentless, invisible pull of their dark foundations. Picture a city skyline at night. You see the glittering towers of light, but you do not see the steel girders, the concrete pillars, the hidden foundation that gives each building its shape and stability. The luminous stars and galaxies we observe are like those city lights. The dark matter is the unseen framework that determines where they can form and how they are structured. It is a humbling thought that the vast majority of the universe's mass, the very thing that built our cosmic home, remains completely invisible to us. We are left to trace its outline by the glow of what it holds. So as the first luminous objects began to flicker on, they were not appearing at random. They were igniting at the precise intersections of this dark matter web, illuminating a structure that had been growing in the shadows for hundreds of millions of years. What did these first true galaxies look like, and how did they begin to organize the once featureless cosmos? These first galaxies were not gentle assemblies of suns. They were chaotic, violent nurseries, and at their hearts burned engines of unimaginable power. The first stars to ignite within them were titans, monsters in a class of their own. Formed from a universe that was pure hydrogen and helium, completely free of the heavier elements we call metals, these primordial stars could grow to staggering sizes. They were not merely large, they were behemoths, some reaching several hundred times the mass of our own sun. A star of such scale is a different kind of object entirely. It burns at a ferocious temperature, shining with a brilliance millions of times more intense than the sun, but it pays a terrible price for its glory. Its immense nuclear furnace consumes its fuel in only a few million years, a mere heartbeat in cosmic time. Their lives were spectacular, but their deaths were even more consequential. When these stellar giants finally exhausted their fuel, their cores collapsed, triggering cataclysmic supernova explosions of a violence we can scarcely comprehend. These were not ordinary supernovas. In some cases, the entire star was obliterated, leaving no remnant behind, scattering its freshly forged contents far and wide. In these titanic blasts, the universe received its first real injection of heavy elements. For the first time, carbon, oxygen, iron, and all the other building blocks of planets and life were forged in stellar hearts and then blasted out into the void, enriching the interstellar medium. This was the first step in transforming the cosmos from a simple, pure hydrogen universe into the chemically rich environment we inhabit today. Can you picture the aftermath of such an explosion? A vast shockwave of material and energy ripples out through the primordial gas cloud. This wave does not just spread destruction, it also triggers creation. As it plows into surrounding clouds of hydrogen, it compresses them, seeding new gravitational instabilities that collapse to form the next generation of stars. This new wave of stars was different. They formed from gas that was now lightly sprinkled with metals, which made the gas more efficient at cooling. This allowed them to form at smaller, more stable sizes, much more like the stars we see today. The cycle of star birth, death, and rebirth had begun, a cycle initiated by the short, violent lives of the very first stellar giants. What do the remnants of these ancient monsters tell us about the early cosmos? We have not yet directly observed one of these first stars, but we see their fingerprints everywhere. Astronomers study the oldest, most metal-poor stars in our own galaxy, ancient relics that formed from the material enriched by just one or two of those first supernova. Their unique chemical composition is a time capsule, a record of the specific nuclear reactions that occurred inside the universe's first stellar furnaces. The existence of these primordial giants also explains the supermassive black holes we find at the centers of nearly every large galaxy. How did such massive objects form so quickly? The most likely explanation is that they grew from the collapsed cores of the very first supermassive stars, giving them a colossal head start. So these first stars were more than just sources of light. They were the universe's first chemists and architects. Their brilliant lives carved out the first clearings in the cosmic fog, and their explosive deaths built the foundation for everything to come, from rocky planets to life itself. As this cycle of stellar birth and death began to organize the cosmos on a local scale, a much larger pattern was also beginning to emerge from the darkness. How did these initial galactic building blocks begin to connect with one another? These initial galactic building blocks were far from the majestic spirals we know today. They were small, irregular blobs of gas and stars, swirling in the gravitational wells of their dark matter halos. Their formation was a chaotic dance, driven by a process astronomers call hierarchical merging. Picture a cosmic downpour where individual raindrops of gas and dark matter begin to fall into gravitational potholes. These droplets merge into streams, the streams flow into rivers, and the rivers eventually converge into vast lakes. In the early universe, small proto-galactic clumps constantly collided and merged, building larger and larger structures over billions of years. It was a violent, ongoing construction project on a cosmic scale. Gravity was the foreman, orchestrating the accretion of gas from the intergalactic medium and the relentless merging of these infant galaxies. How can we possibly witness such ancient events? Our most powerful telescopes give us a direct window into this era. The Hubble Space Telescope's deep field images, for instance, revealed thousands of faint smudges of light, each one a galaxy seen as it was in its infancy. These observations show us a universe that looks fundamentally different, filled with smaller, more irregular, and often clumpy galaxies caught in the very act of formation. One of the most distant galaxies we have ever observed, known as GNZ11, serves as a perfect snapshot of this primordial time. We see it as it was just 400 million years after the Big Bang. It is small, incredibly bright, and forming stars at a furious rate, a classic example of an early galaxy in its raw, initial stage of growth. Over immense stretches of time, these chaotic blobs began to settle. The relentless mergers and the steady accretion of fresh gas provided both the material and the angular momentum needed for structure to emerge. Some galaxies, through peaceful accretion of gas from their filaments, began to spin faster, their material flattening into vast, rotating disks that would become spiral galaxies like our own Milky Way. Others experienced more violent mergers. Their gravitational fields stirred into a frenzy, randomizing the orbits of their stars and creating the smooth, featureless ellipsoids we classify as elliptical galaxies. The entire cosmos was transforming from a formless sea of gas into a structured network of cosmic cities. The universe was no longer a blank, dark canvas. It was becoming a tapestry of light and matter, each thread woven by the invisible hand of gravity. This interplay between the luminous and the dark, between the structures we can see and the framework we cannot, is the final piece of the puzzle. How did this emerging cosmic web ultimately dictate the large-scale architecture of everything that exists? This emerging structure is the cosmic web, the largest pattern in existence. Our universe is not a random scattering of galaxies. It is a vast, interconnected network. Picture a colossal spiderweb spun across billions of light years, with brilliant knots of galaxies clustered at the intersections, connected by long, delicate filaments of dark matter and gas. Between these threads lie the cosmic voids, unimaginably vast and nearly empty deserts of space. This is the grand architecture that began to crystallize during the universe's Middle Age. The invisible scaffolding of dark matter formed first, and ordinary baryonic matter, the stuff of stars and planets, simply followed its lead, flowing along these gravitational highways. Supercomputer simulations, like the famous Millennium Run, allow us to watch this process unfold. They begin with the tiny fluctuations from the Big Bang, and then fast forward through billions of years, showing dark matter coalescing into an intricate, web-like pattern that matches the large-scale structure we observe with our telescopes today. It is a humbling confirmation that we understand, at least in broad strokes, how the cosmos built itself. You can think of it as the universe's neural network, or the root system of a forest on a cosmic scale, with galaxies growing like fruits at the points where the roots intersect. At the densest nodes of this web, where multiple filaments meet, we find the most massive structures in the universe, galaxy clusters. These are cities of thousands of galaxies, all bound together by gravity, swimming in a sea of superheated gas that glows in X-rays. Their immense gravity acts as a cosmic lens, bending the light from even more distant objects behind them, and providing us with another way to map the unseen dark matter that holds it all together. We are living inside this web. Our own Milky Way galaxy resides within a filament, part of the local group, which is itself being pulled toward the Great Virgo cluster, one of the major nodes in our cosmic neighborhood. Every time you look up at the night sky, you are looking out into this immense structured network, a design whose foundations were laid in the profound silence of the cosmic dark ages. As this vast architecture solidified, a final transformation was needed to make it visible. light had to learn to travel. These brilliant beacons from the early universe are known as quasars, the most persistently luminous objects in the cosmos. A quasar is not a star, but the incredibly bright core of a distant galaxy, powered by a supermassive black hole that is actively feeding. As vast quantities of gas spiral into the black hole, the material forms a searingly hot accretion disk that can outshine its entire host galaxy by 1,000 times. In the era of reionization, these objects were not just spectacular light sources, they were active participants in clearing the cosmic fog. Their intense radiation acted like a cosmic blowtorch, helping to strip electrons from the neutral hydrogen atoms and carve out vast, transparent bubbles in the intergalactic medium. One astrophysicist described their spectra as the ultimate cosmic barcode. When we analyze the light from a quasar that has traveled for over 13 billion years to reach us, we see a complex pattern of absorption lines. Each dip and spike in that light tells a story, revealing the composition and state of the diffuse gas clouds it passed through on its long journey. This allows us to probe the conditions of the universe during its middle age, mapping the distribution of neutral hydrogen and watching as the transparency of the cosmos increased over time. A stunning example is the quasar known as ULSJ 1342+0928. This is one of the most distant quasars we have ever found, a beacon shining when the universe was only 690 million years old. Its light carries the unmistakable signature of a cosmos that was still partially cloaked in neutral hydrogen, offering us a direct snapshot of the final stages of the reionization epoch. How did these cosmic lighthouses influence the evolution of the very first galaxies around them? Their intense radiation and powerful jets could have either triggered star formation by compressing nearby gas clouds, or they could have stifled it by blowing that vital raw material away. They were the ultimate regulators, their influence shaping the growth of galactic structures from the very beginning. The light from these quasars serves as a perfect time capsule, a direct messenger from an era when the universe was still forging its identity. As we study their ancient light, we are not just looking at the beacon itself, we are reading the history of everything that light has touched. This forces us to ask a deeper question about the medium through which that light traveled for so long. What is the true nature of the space between the galaxies, and how did this intergalactic medium evolve from a simple sea of hydrogen into the complex cosmic web we see today? This intergalactic medium is the very fabric of space itself, a diffuse ocean of gas that fills the unimaginable voids between galaxies. It is not a perfect vacuum, but rather a thin soup of particles, primarily hydrogen, that exists in two fundamental states. Some of this hydrogen remains neutral, with its electrons still bound to the proton, while the majority was permanently ionized during the epoch of reionization, its electrons stripped away to create a hot, thin plasma. This transformation from a neutral fog to an ionized transparency was the single most important event for allowing light to travel freely across the cosmos. Think of a thick morning fog finally burning away under a bright sun, revealing a distant mountain range you never knew was there. The clearing of the intergalactic medium did exactly that for the universe, unveiling the first galaxies and quasars to each other and ultimately to our telescopes. How does this tenuous gas, so sparse it contains only a few atoms per cubic meter, exert any influence at all? Its effects are cumulative and profound. This medium acts as both a cosmic highway and a subtle barrier. It provides the raw fuel for future generations of stars as galaxies continuously accrete gas from these intergalactic filaments. Yet, it can also resist the formation of new structures. The heat and pressure of the ionized gas can prevent small, fragile clumps of matter from collapsing, effectively setting a minimum size for the galaxies that can form. We can actually see the ghostly imprint of this gas etched into the light of the most distant quasars. When astronomers analyze a quasar's spectrum, they do not see a smooth rainbow of color. Instead, they see a forest of absorption lines, a phenomenon known as the Lyman alpha forest. Each one of those dark lines represents a cloud of neutral hydrogen somewhere along the line of sight between the quasar and us. The closer the cloud is to the quasar, the more the light is redshifted, creating a dense thicket of lines that we can decode. It is like listening to a symphony played across billions of light years, where every missing note tells us about a different cloud of gas the music had to pass through. By studying this intricate absorption pattern, cosmologists can create a detailed map of the universe's structure at different epochs. They can trace how the clumpy, neutral hydrogen of the early universe was gradually ionized and heated, watching the dense forest of lines thin out over cosmic time as the fog receded. This intergalactic medium connects everything, a cosmic ecosystem where galaxies are not isolated islands, but vibrant cities that breathe the shared atmosphere of space, drawing in resources and expelling enriched material back out. Understanding this delicate balance forces us to look closer, to employ the most advanced tools ever built to trace the final contours of this ancient story. Our most powerful telescopes are not merely windows into space, but portals into the deep past. The James Webb Space Telescope, for instance, does not see the universe as it is today, but collects ancient photons that began their journey when the cosmos was in its infancy. This incredible feat relies on two fundamental principles: look-back time and redshift. Look-back time is simple to grasp. The farther away an object is, the longer its light has taken to reach us. When we observe a galaxy a billion light-years away, we are seeing it as it was a billion years ago. Redshift is the key to measuring these vast distances. As the universe expands, it stretches the very fabric of space, and the light traveling through it gets stretched along with it. This stretching shifts the light's wavelength toward the red end of the spectrum. The greater the redshift, the farther the light has traveled, and the further back in time we are looking. One astronomer beautifully described it as listening to a symphony where all the notes are slowing down, revealing the age and distance of the cosmic orchestra. To peer into the era of the first stars and galaxies, we must push our vision to extreme redshifts. The Hubble Space Telescope gave us our first deep glimpses, but the James Webb was specifically designed to see further. Its immense gold-coated mirror and infrared-sensitive instruments are perfect for detecting the highly redshifted light from the universe's first luminous objects. Scientists working with Webb data have expressed astonishment at the sheer number of early galaxies it has revealed. We expected a handful of faint, infant systems, but instead we found a cosmos already teeming with activity, suggesting that galaxies assembled with a speed and efficiency that challenges some of our previous models. It is like peeling back the layers of a cosmic onion, each layer revealing an earlier, more primitive chapter in the story of structure. Specific missions have each contributed a piece of this puzzle. The Planck satellite meticulously mapped the cosmic microwave background, giving us the baby picture of the universe. Hubble's deep field observations then showed us the childhood and adolescence of galaxies. Now, Webb is showing us the universe in its turbulent toddler years, a time of rapid growth and transformation. Its spectroscopic data is allowing us to analyze the chemical composition of these primordial galaxies, confirming they are indeed low in heavy elements, just as our theories of the first star formation predicted. What will future telescopes, like the planned Nancy Grace Roman Space Telescope, reveal about this forgotten age? They may be able to directly detect the very first populations of stars, or even map the faint glow of reionization itself. watching as the first brilliant bubbles of ionized gas began to pop and merge across the cosmos. This relentless push to see further back is not just about finding older objects. It is about understanding the very moment the universe switched on the lights and began its long journey toward chemical complexity, a journey initiated by the explosive deaths of those first stellar giants. Those first supernovae were cosmic alchemists, transforming the simple universe into something new and complex. Deep within the hearts of those primordial stellar giants, under conditions of immense pressure and heat, nuclear fusion was doing more than just generating light. It was forging the very first heavy elements. The process began with hydrogen fusing into helium, but in stars hundreds of times more massive than our Sun, the fusion chain continued relentlessly. Helium atoms fused into carbon, carbon into oxygen, and so on, climbing the periodic table all the way up to iron. This process, known as stellar nucleosynthesis, was the universe's first kitchen. But the true cosmic feast came in the explosion, the cataclysmic violence of a pair-instability supernova, which could utterly obliterate the star, flung these newly forged elements out into the void at incredible speeds. For the first time, clouds of pure hydrogen and helium were seeded with carbon, nitrogen, oxygen, and iron. This was the critical enrichment of the interstellar medium, the moment the universe gained the raw ingredients for planets, for oceans, and for life itself. Think of it as a master chef after a spectacular culinary explosion, scattering precious spices and flavors throughout a once bland kitchen, making all future meals infinitely richer. We have direct evidence of this first cooking session in the oldest stars of our own galaxy. Astronomers study stars like He 152300901, a celestial relic in the halo of the Milky Way. Its light reveals an almost complete absence of iron and other heavy elements. Its chemical fingerprint is a pristine record of being formed from material enriched by just one or two of those first supernovae. The specific abundance patterns in such stars, for instance a surprising amount of carbon relative to iron, tell us about the unique nuclear reactions that occurred inside those first stellar furnaces, reactions different from those in stars today. Every time you take a breath, you are inhaling oxygen atoms that were forged in a star that died billions of years ago. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your DNA, all of it was synthesized in the heart of a long-dead star and scattered across the galaxy by its final, glorious explosion. We are not just living in the universe, we are literal stardust, the temporary assembly of atoms that began their journey during the universe's forgotten Middle Age. This cosmic chemistry set the stage for the next great act, as these newly enriched clouds of gas began to collapse into a new generation of stars, this time surrounded by the rocky material that would become planets. How did this enriched material lead to the mature, structured galaxies we recognize today? The universe's youth was a time of spectacular collisions and chaotic growth. Young galaxies, drawn together by their immense dark matter halos, did not evolve in peaceful isolation. They crashed, merged, and cannibalized one another in a relentless gravitational dance. These cosmic pile-ups were the primary engine of galactic evolution, triggering incredible bursts of creation and destruction that shaped the sizes and forms of the galaxies we see today. When two gas-rich proto-galaxies collided, it was not a simple crunch of stars. Their vast clouds of interstellar gas smashed together, compressing into incredibly dense, turbulent regions. Within these cosmic pressure cookers, gravity rapidly seized the opportunity, collapsing countless pockets of gas into new stars all at once. This is what astronomers call a starburst, a ferocious baby boom of stellar birth that could light up a galaxy, outshining its entire previous history. These starburst galaxies are the rock stars of the early universe, living fast and dying young, consuming their fuel in a blaze of glory. The violence did not stop with star formation. These galactic mergers also funneled enormous amounts of gas directly toward the central supermassive black holes lurking in each galaxy's core. As this gas spiraled inward, it formed a blazingly bright accretion disk, transforming the black hole into an active galactic nucleus, a quasar whose radiation could outshine the combined light of billions of stars. For a time, this single engine at the heart of a merging galaxy became the most powerful beacon in the cosmos. We can see the evidence of this turbulent past etched across the sky. In Hubble's deep field images among the serene spirals, we find galaxies with bizarre, distorted shapes, sporting tidal tails of stars stretched out like cosmic taffy. These are the survivors of recent collisions, their structures still reeling from the impact. It is like looking at the wreckage of a car crash, frozen in time, telling a clear story of a violent encounter. Supercomputer simulations bring this entire process to life. They show dark matter halos acting as gravitational guides, bringing their luminous galactic contents together. We watch as two distinct blobs of stars and gas swing past each other, their gravity intertwining, pulling long streams of material into space before they finally coalesce into a single, larger, and often more elliptical galaxy. This hierarchical merging is how small galactic building blocks grew into the majestic giants we see today. Picture two small towns, each with their own quiet pace, suddenly merging into a sprawling, chaotic metropolis. The collision creates new infrastructure, a burst of frantic construction, and a central powerhouse that dominates the entire region. This is precisely what happened on a galactic scale. How does such violence breed the beautiful structures we admire? The chaos of the merger randomizes the orderly orbits of stars, wiping away delicate spiral arms and puffing the galaxy up into a smooth, round ellipsoid. The largest elliptical galaxies we see are likely the products of multiple such mergers, cosmic megalopolises built from the remains of many smaller cities. Every massive galaxy we see, including our own Milky Way, carries the scars and the legacy of this aggressive adolescence, a history written in the motions of its stars and the dormant giant at its center. This entire growth spurt was orchestrated by an unseen hand, guided by the mysterious dark components that make up the bulk of the cosmos. Yet another invisible hand was shaping the cosmic landscape from the very beginning. While dark matter provided the gravitational pull to build structures, a more mysterious force was already at work, pushing them apart. This is dark energy, a repulsive force woven into the fabric of space itself, driving the universe's accelerated expansion. For a long time, we thought its influence was a recent development, but cosmologists now debate its subtle role even during the universe's Middle Age. One leading researcher noted that dark energy might have been a quiet background actor on the cosmic stage, its gentle pressure already influencing how quickly the cosmic web could form. Think of it as an invisible tide, slowly and imperceptibly pulling islands in an archipelago away from one another, making it just a little harder for them to form bridges and trade material. This subtle push would have affected the rate of galaxy clustering. In a universe without dark energy, gravity would have continued to pull matter together more efficiently, potentially creating an even denser cosmic web than the one we see today. Dark energy acted as a cosmic regulator, gently opposing gravity's relentless pull and setting a limit on how large structures could grow. We have two key observational pillars that reveal dark energy's dominance. The first comes from distant supernova. In the late 1990s, astronomers measured these exploding stars to gauge the expansion rate of the universe over time. To their astonishment, they found that the expansion was not slowing down due to gravity, as everyone expected, but was instead speeding up. This was the direct signature of dark energy's push. The second pillar is Baryon acoustic oscillations. These are frozen sound waves from the early universe, imprinted in the large-scale distribution of galaxies. They act as a standard ruler. By measuring the apparent size of these oscillations at different cosmic epochs, we can trace how the expansion history of the universe has changed, confirming that dark energy became the dominant force about 5 billion years ago and was likely a persistent, if weaker, presence long before. How did this force shape the grand architecture we inherited? It dictated the final form of the cosmic web, determining the scale of the vast voids and the maximum size of the great galaxy clusters. As this invisible tide continued to rise, it began to influence another, more delicate aspect of the cosmos, the subtle magnetic fields that would one day thread through the voids between the galaxies. While dark energy shaped the grand stage, another invisible force was threading its way through the cosmic web. Primordial magnetic fields, faint relics from the universe's earliest moments, may have subtly guided the flow of gas and the birth of the first stars. These are not the organized fields of a simple bar magnet, but a vast, tangled web of force lines woven through the very fabric of space. Their origins are lost in time, possibly sparked by violent phase transitions in the searing plasma of the infant cosmos, or later, by the turbulent winds from the first supernova. One theoretical physicist describes them as the universe's invisible skeletons, providing a subtle structure that influenced how matter could move. In the Dark Ages, these fields were unimaginably weak, but as gravity gathered the first clouds of gas, the fields were compressed and amplified along with them. Picture a handful of loose threads being drawn together into a taut, strengthening rope. This process could have been crucial within proto-galactic clouds. As gas collapsed to form stars, these magnetic fields would have exerted a gentle pressure, resisting gravity's pull in some regions and channeling flows of plasma in others, effectively acting as a cosmic regulator for the efficiency of star formation. We cannot see these fields directly, but we can detect their ghostly imprint. As light from the early universe travels through space, it can become polarized, its waves aligned in a specific direction by interacting with magnetized plasma. By studying the polarization of the cosmic microwave background with exquisite precision, observatories like the Simons Observatory are hunting for the faint swirls and patterns that would be the signature of these primordial fields. Another clue comes from cosmic rays, high-energy particles racing across the universe. These particles do not travel in straight lines, but spiral along the invisible pathways of magnetic fields. By tracing the arrival directions of these rays, we can indirectly map the field lines that guide them, like watching leaves caught in a stream to understand the water's current. These fields were the universe's first infrastructure, guiding the movement of material on a colossal scale and helping to shape the complex, structured cosmos we inherited. Their silent, persistent influence reminds us that the universe is governed by forces we are only beginning to perceive. This hidden architecture set the stage for an even more profound shift as the cosmos began to transition from a collection of simple structures into a system of breathtaking complexity. Deep within those first chaotic galaxies, gravity was forging its ultimate traps. The most massive of the primordial stars, those behemoths hundreds of times the weight of our sun, lived short, violent lives. When their nuclear fuel was exhausted, their cores collapsed catastrophically. For the very largest, this collapse was so immense that not even a neutron star could form. Instead, the entire core crushed itself into a point of infinite density, creating the universe's first stellar mass black holes. Another, more mysterious path may also have existed. In the densest regions of dark matter, vast clouds of pure hydrogen gas might have collapsed directly, bypassing the star stage entirely to form black hole seeds thousands of times more massive from the very beginning. These were the primordial seeds of all future cosmic power. These newborn black holes were not yet the supermassive giants we know today. They began a slow, relentless feast. Anchored by gravity at the hearts of their host protogalaxies, they pulled in vast streams of surrounding gas. As this material spiraled inward, it formed a searingly hot, luminous disk around the black hole's event horizon, transforming it into an active galactic nucleus. The most brilliant of these became quasars, beacons that could outshine entire galaxies. Through mergers with other black holes and continuous feeding, these seeds grew over billions of years into the supermassive black holes, weighing millions or even billions of solar masses that now reside at the center of nearly every large galaxy. Their growth and the galaxy's growth became an intertwined cosmic dance. But these black holes were not passive consumers, they became powerful regulators. Their intense radiation and blistering particle jets poured a colossal amount of energy back into the surrounding galaxy. This is known as feedback, a cosmic balancing act of breathtaking power. In one mode, this feedback could be constructive. The shockwaves from jets and radiation could compress enormous clouds of gas, triggering intense bursts of new star formation and effectively building the galactic core. In another mode, it could be utterly destructive. The same forces could heat the galactic gas reservoir to such extremes that it could no longer collapse to form new stars, or it could blast the gas entirely out of the galaxy, starving it of the raw material for future generations of suns. This process, known as quenching, could effectively shut down a galaxy's main engine of growth. We see this dramatic interplay in the early quasars, RULSJ 1342. Its brilliant light suggests a supermassive black hole in a phase of intense growth, likely pouring energy into its host galaxy. The question is, was this energy triggering a firestorm of stellar birth, or was it beginning to sterilize its own home? The answer likely depends on the precise balance between the black hole's appetite and the galaxy's available gas. A black hole could act as a galactic heart, pumping energy through the system to stimulate growth, or it could become a cosmic vampire, draining the lifeblood from its surroundings. How did these opposing forces of creation and destruction shape the diverse population of galaxies we see in the modern universe? The legacy of these ancient gravity wells is written across cosmic time. Galaxies with overly massive black holes for their size often show signs of this past violence, their star formation histories cut short. The most massive elliptical galaxies we see today, full of old red stars, are likely the products of this precise feedback mechanism, their gas supplies depleted by the ferocious activity of their central black holes in the distant past. These cosmic engines did not just dwell within their galaxies, they fundamentally shaped their fates, their immense gravity dictating the rhythm of stellar birth and death from the very center of power. As these titans carved out their domains, they were also illuminating the final transformation of the cosmos itself, a clearing of the fog that would reveal the grand cosmic web for the very first time. The cosmos of the Middle Age was a landscape of stunning contrasts, a patchwork of environments that dictated the fate of every galaxy within them. On the largest scales, gravity had sculpted the universe into a tapestry of immense voids and brilliant clusters. These were the cosmic habitats ranging from sparse, lonely deserts to densely packed metropolitan hubs. Vast cosmic voids, regions hundreds of millions of light years across, contained almost nothing. A galaxy stranded in such a place was an isolated island, cut off from the flows of intergalactic gas that fueled star formation, destined for a quiet, solitary existence. In stark opposition stood the galaxy clusters, the great cities of the cosmos. Here, thousands of galaxies swarmed together, bound by the immense gravity of their combined dark matter halos, swimming in a searing ocean of plasma that glowed with X-rays. A galaxy living here experienced a life of intense social interaction, constant gravitational encounters, and fierce competition for resources. Grand surveys of the sky, like the Sloan Digital Sky Survey, have meticulously mapped the positions of millions of galaxies, revealing this cosmic geography in breathtaking detail. Their three-dimensional maps show the delicate filaments of the cosmic web, the vast empty bubbles of the voids, and the dense, sparkling knots where clusters reside. This is the large-scale structure that emerged from the Dark Ages, a blueprint written by gravity and revealed by light. The environment a galaxy found itself in became the single greatest factor in its evolution. A galaxy forming in an isolated, rural filament could grow steadily through a peaceful diet of cold gas, its rotation undisturbed, allowing it to mature into a grand spiral. But a galaxy born into or falling into a dense cluster faced a far more violent destiny. One of the most dramatic mechanisms at work is ram pressure stripping. As a spiral galaxy plunges at millions of miles per hour through the superheated plasma that fills a cluster, it experiences a cosmic wind of unimaginable force. This wind acts like a powerful river current, violently stripping away the galaxy's own reservoir of cold gas, the very raw material needed to form new stars. The galaxy is effectively robbed of its future, its star formation quenched as its spiral arms slowly fade. We see the evidence of this today in clusters like Virgo, which are filled with red and dead elliptical galaxies, their blue star-forming spirals long since stripped and transformed. It is a celestial example of how location dictates destiny. A galaxy's fate was sealed not just by its own mass or the black hole at its center, but by its cosmic zip code. Was it a quiet town or a bustling, violent metropolis? This environmental pressure, combined with the internal feedback from supernova and black holes, created the rich diversity of galaxy types we catalog in the night sky. As these structures solidified and galaxies found their place within the cosmic web, a final, brilliant transformation was underway, one that would fill these diverse environments with a glow that had not been seen since the universe's first instant. This cosmic backdrop was not a static curtain, but a stage undergoing a dramatic transformation of its own. For millions of years after the Big Bang, the only background light was the faint, cooling glow of the cosmic microwave background, a uniform bath of microwave radiation. But as the first stars and quasars ignited, they flooded the universe with a new kind of light, creating a pervasive cosmic ultraviolet background. Imagine the universe as a vast theater just before a performance. The CMB was the house lights, dim and even. Then the first luminous objects appeared like individual spotlights flickering on. As more and more of them ignited, their combined ultraviolet radiation merged into a new, diffuse glow that filled the entire cosmos, like the stage lights brightening to reveal the set. This was not a gentle illumination, it was a powerful, ionizing force. One researcher described this ultraviolet background as a cosmic fog lamp, its intense photons stripping electrons from hydrogen atoms across the vast intergalactic medium. This process kept the universe transparent, but it also exerted a profound influence on the formation of the next generation of galaxies. The radiation heated the diffuse gas, making it harder for small, fragile proto-galaxies to pull in enough material to collapse and form stars. It essentially set a cosmic minimum size for galaxy formation, suppressing the birth of tiny dwarf galaxies and favoring the growth of larger systems. How do we observe this ancient, all-pervading light that has long since faded? We see its ghostly signature in the Lyman alpha forest, the intricate pattern of absorption lines in quasar spectra. The density and character of this forest are a direct record of the ultraviolet background's intensity. Where the background radiation was strong, it ionized more hydrogen, creating wider gaps between the absorption lines, like a bright light burning holes in a dense fog. In regions where the radiation was weaker, the forest of lines remains thick and dense. By meticulously mapping these patterns, astronomers can trace the history of this cosmic glow, watching as it built from a few faint flickers into a brilliant, all-encompassing radiance. This evolving background was the final brushstroke in the universe's transformation from a dark, simple expanse into a structured, luminous cosmos. Its pervasive influence carved the conditions for galactic life, determining which structures would thrive and which would fade away. How did this universal shift from darkness to light mark the beginning of a new, irreversible direction for cosmic history itself? Pinpointing the exact dates of this cosmic dark age is a detective story written in light and shadow. Astronomers do not use a single calendar, but a toolbox of interlocking methods to build a precise timeline for the universe's adolescence. The most fundamental of these tools is redshift, a direct consequence of the expanding universe. As light travels across the vast, stretching cosmos, its wavelengths are stretched, shifting toward the red end of the spectrum. The greater the redshift, denoted by the letter Z, the farther the light has traveled and the further back in time we are looking. A galaxy at a redshift of 6, for example, is seen as it was when the universe was only around 1 billion years old. This is our primary ruler for measuring cosmic distances and epochs. But to understand what was happening within those early galaxies, we need another kind of clock. This is where chemical clocks come into play. The oldest stars in our own Milky Way act as cosmic fossils, their atmospheres preserving the chemical composition of the gas cloud from which they formed. Stars with almost no heavy elements, like He 152300901, must have been born from material enriched by only the very first generation of supernova. By dating these ancient stars using their nuclear decay, a technique called nucleocosmochronology, we can establish a minimum age for the universe itself and trace the timeline of those first stellar explosions. It is similar to how geologists use radioactive isotopes in rocks to date the Earth, or how we count tree rings to understand the history of a forest. Each stellar generation leaves a distinct chemical fingerprint, a layer in the cosmic strata. Another powerful technique is stellar population modeling. By analyzing the combined light of a distant galaxy, astronomers can pick apart the ages of its stars. A galaxy whose light is dominated by short-lived, brilliant blue giants is clearly young, still in a ferocious starburst phase. A galaxy whose light is redder and comes from longer-lived, older stars indicates a system that formed its stars much earlier. By fitting models to this light, we can estimate when the main burst of star formation in that galaxy began, effectively dating its birthday. These methods collectively point to key transitional events. The end of the Reionization epoch, for instance, is dated to a redshift of roughly 6, when the universe was about 1 billion years old. We know this because the light from quasars at higher redshifts shows the thick absorption of a neutral universe, while light from slightly later times travels more freely. It is like finding a layer of ash in the geologic record that marks a global fire, a definitive moment when everything changed. One leading cosmologist compares the challenge to reconstructing the history of an ancient city from scattered ruins and pottery shards, where every fragment tells a partial story. The uncertainties are real, but each new observation from telescopes like James Webb sharpens the timeline, reducing the margin for error. This forces us to think of time not as a simple ticking clock, but as a dimension of the universe itself, a river flowing from the Big Bang to the present. Just as a tall building casts a long shadow, these first immense structures cast shadows across time, and by studying their faint outlines, we can measure the very fabric of the cosmos. Every beam of quasar light is a messenger carrying secrets from the cosmic dark age. As this ancient light journeys for billions of years toward our telescopes, it does not travel through empty space. It passes through clouds of neutral hydrogen, the leftover ghosts of the primordial universe. Each cloud it encounters leaves a unique mark, a dark line etched into the quasar's rainbow-like spectrum. These are absorption lines, the shadows of cosmic structures cast upon a brilliant beacon. When astronomers point their most powerful spectrographs at a quasar, they do not see a clean, continuous band of color. Instead, they see a forest. The Lyman alpha forest is a dense thicket of thousands of dark absorption lines, each one a silhouette of a single hydrogen cloud that the quasar light had to pass through on its long journey to Earth. The pattern of this forest is a direct record of the universe's structure at different epochs. A dense tangle of lines means the light passed through a region still rich in neutral hydrogen, a relic of the earlier, foggier universe. Wider gaps in the forest signify vast, ionized bubbles where the ultraviolet light from early galaxies and quasars had already burned through the fog, creating transparent regions. It is like reading the diary of the cosmos, where every missing line of light tells a story about a different chapter in the Great Clearing. Some of these shadows are deeper and broader than others. Damped Lyman alpha systems represent the grand reservoirs of the early cosmos. These are not wispy clouds, but massive, dense concentrations of cold hydrogen gas, so thick they completely absorb the quasar's light at a specific wavelength. Astronomers believe these are the direct progenitors of modern galaxies, vast rotating disks of pristine gas in the process of collapsing to form their first stars. They are the cosmic fuel tanks from which entire galaxies were built. By counting these different absorbers and mapping their redshifts, scientists can create a three-dimensional chart of the universe's matter distribution. They can watch the forest thin out over cosmic time, tracing the precise history of reionization as the shadows of neutral hydrogen slowly retreat. What do these ancient silhouettes hide within their dark profiles? They conceal the subtle feedback cycles already at work, the delicate balance between gas collapsing to form stars and the fierce radiation from those same stars blowing the gas away. These shadows are not just passive markers, they are the fingerprints of the universe's first attempts to regulate its own growth, a self-imposed order emerging from the primordial chaos. These brilliant cycles of creation and destruction were governed by cosmic thermostats. Across the early universe, two primary feedback mechanisms worked in tandem to regulate the growth of galaxies, maintaining a delicate equilibrium between furious construction and sudden shutdown. The first thermostat was supernova winds. When massive stars died in violent explosions, they did not simply fade away. They drove powerful shockwaves through their host galaxy, heating vast clouds of interstellar gas to extreme temperatures and often blasting it completely out into intergalactic space. This stellar feedback, as it is called, could both trigger new star formation by compressing nearby gas and simultaneously quench it by removing the very fuel required. It was a self-limiting process, a natural brake on runaway stellar birth. The second, even more powerful thermostat was controlled by the supermassive black holes at the galactic centers. As these black holes fed, they could unleash tremendous outflows of energy and matter, known as active galactic nucleus, or AGN feedback. These colossal jets and radiation could heat the surrounding gas halo so effectively that it could no longer cool and collapse to form stars, effectively shutting down the galaxy's main engine for millions of years. Supercomputer simulations reveal the stunning precision of this balance. Models that include these feedback processes produce virtual galaxies with sizes, shapes, and masses that perfectly match our real-world observations. Without feedback, galaxies in simulations grow far too large and massive, forming stars at unrealistic rates. The feedback loops act as a regulatory system, ensuring no single galaxy consumes all the available resources. We can witness this cosmic regulation in our own cosmic backyard. In the nearby galaxy M82, astronomers observe a massive superwind, a fountain of hot gas and heavy elements being violently ejected from the galactic disk by the combined force of thousands of supernovae. This is negative feedback in action, a galaxy actively expelling the material it needs for its own future growth. Conversely, in some systems, the shockwaves from AGN jets are seen compressing cold gas clouds, triggering the birth of new star clusters along their path. This is positive feedback where destruction directly begets creation. How do these opposing forces maintain a cosmic equilibrium? They prevented galaxies from either burning out in a brief, furious blaze or growing into unchecked leviathans. The most massive galaxies we see today are those where the central black hole effectively shut down star formation long ago, leaving a population of old, red stars. The thermostat clicked off and the galaxy entered a quiet retirement. This self-regulation was fundamental to creating the diverse zoo of galaxies we catalogue. It was a universal principle, a dance of energy that ensured the cosmos could not only ignite but could also sustain itself. As these cycles settled into a rhythm, the universe itself began to brighten, its gradual illumination marking the end of the long, formative darkness. This final clearing of the cosmic fog was not a single, sudden flash, but a drawn-out dawn breaking across an entire universe. The epoch of reionization concluded when the last great pockets of neutral hydrogen were finally split apart, rendering the cosmos permanently transparent to ultraviolet light. This transition did not happen everywhere at once. Some regions, illuminated by dense clusters of early galaxies or brilliant quasars, became clear bubbles of ionized plasma hundreds of millions of years before the more isolated, rural voids. The universe was a global landscape experiencing a staggered sunrise, where the last vestiges of primordial shadow lingered in the deepest cosmic hinterlands. We have a ghostly photograph of this final act imprinted on the oldest light we can see, the cosmic microwave background radiation that afterglow from the Big Bang carries a faint pattern of polarization, a specific alignment of its light waves. This polarization is a direct relic of that last scattering, when the CMB photons finally broke free from the plasma. As one researcher involved with the Planck satellite mission explained, the specific swirls in this polarization are a cosmic signature, telling us that the universe was reionized to a specific degree and that the process was largely driven by the first populations of stars and galaxies, not by quasars alone. While quasars were the brilliant blowtorches, their numbers were too few to account for the entire reionization of the cosmos. The true heroes were the countless faint, early galaxies, their collective ultraviolet output forming a diffuse, all-pervading glow that slowly and steadily burned away the fog. Observations of so-called Lyman alpha emitter galaxies provide a crucial constraint. These are galaxies whose light is predominantly emitted at the specific wavelength a hydrogen atom releases when an electron falls back into place. In a fully neutral universe, this light would be absorbed before it could travel far. The fact that we can see these emitters from increasingly early times tells us that by a redshift of around 6, vast transparent bubbles had already formed, allowing their distinctive light to escape and journey across the cosmos. It is like seeing the lanterns of distant villages begin to shine through a lifting mist, confirming that the air is clearing. This pivotal ending, the moment the last patch of neutral hydrogen was ionized, marked a fundamental shift. The universe's dark age was irrevocably over. The cosmic stage was now fully set, its backdrop clear, its architecture revealed. The legacy of this great thaw is the transparent, structured universe we inhabit today, a cosmos where light can travel for billions of years to tell us its ancient story. The legacy of that formative era is written into the very fabric of our night sky. Every spiral galaxy, every elderly star cluster, and every planetary system is a direct inheritance from the universe's forgotten Middle Age. The diversity we see today, from majestic spirals to smooth ellipticals, was predetermined by the initial conditions of that dark time. The slight density ripples frozen in the cosmic dawn were the blueprints, and dark matter provided the unseen framework upon which this entire cosmic city was built. The size and shape of a galaxy's dark matter halo acted as a cosmic mold, dictating whether it would become a grand, rotating disk or a featureless sphere of stars. One leading cosmologist describes this as a galactic family tree, where the chaotic mergers and quiet growth of those first proto-galaxies are the ancestral roots that determine the destiny of their descendants billions of years later. Our own Milky Way is a living relic of this process. Its vast halo of ancient stars and its distinct spiral arms tell a story that began with a small dark matter seed in the early cosmos, one that grew through countless mergers and steady accretion, a history directly tied to the events of that primordial epoch. The chemical fingerprints of that time are all around us and within us. The element abundances we measure in the sun and in meteorites are a direct consequence of those first supernova explosions. The specific mix of carbon, oxygen, and iron available when our solar system formed was determined by billions of years of stellar life and death, a cycle initiated during the Middle Age. This predetermined the very possibility of rocky planets like Earth. Without that early enrichment by the first stellar generations, the cosmos would contain only gas giants, with no solid ground for life to ever take root. How did these foundational processes lead to the organized classification of galaxies we see today? The Hubble sequence itself, that iconic tuning fork of spiral and elliptical galaxies, is a direct result of the interplay between dark matter halo formation, merger history, and the regulating feedback from supernova and black holes. A galaxy that experienced a violent, merger-heavy youth likely became an elliptical. A galaxy that grew peacefully through the steady accretion of gas along a filament retained its spin and flattened into a spiral. We are left to ponder our own cosmic inheritance. The atoms that form our world were forged in stars that died during that ancient era, and the galaxy we call home was shaped by gravitational forces set in motion before the first star ever shone. What other unsolved mysteries remain hidden within the faint light from this foundational chapter of cosmic history? Despite the grand story we have pieced together, profound gaps remain in our cosmic history. The universe's middle age is still shrouded in mystery, with fundamental questions that challenge our understanding of physics itself. We have not yet directly observed a single one of those first monstrous stars, known as population 3 stars. Their existence is a cornerstone of our theories, but it remains a theoretical prediction. Did they truly form as colossal behemoths, or could the first stellar generation have included a wider variety of sizes? Their definitive signature continues to elude our most powerful telescopes. Another great puzzle is the precise timeline of reionization. We know it happened, but its details are murky. Was it a swift and dramatic revolution, or a slow and gradual dawn? Different observations seem to tell slightly different stories, leaving cosmologists to debate whether galaxies or quasars played the dominant role in clearing the cosmic fog. As one astronomer working with James Webb data remarked, it is like trying to map a forest fire from the pattern of the surviving trees without having seen the flames themselves. The origins of supermassive black holes present perhaps the most startling mystery. How did these giants weighing billions of suns form so quickly after the Big Bang? Did they grow from the remnants of the first stars, or were they born large from the direct collapse of immense gas clouds in the early universe? We simply do not know the seed from which these cosmic monsters sprouted. And underpinning all of this is the enduring enigma of dark matter. We can map its gravitational influence with incredible precision, but we have no idea what it actually is. Is it a yet undiscovered particle, or does it point to a need to revise our fundamental understanding of gravity? Each of these questions is a critical missing piece in our vast cosmic puzzle. Upcoming missions are being designed specifically to hunt for these answers. The Nancy Grace Roman Space Telescope will conduct wide-field surveys to find the very first galaxies and trace the distribution of dark matter with unprecedented clarity. The Laser Interferometer Space Antenna, LISA, will listen for the gravitational wave ripples from the mergers of those first supermassive black holes, potentially revealing their birth cries. On the ground, enormous telescopes like the Extremely Large Telescope will dissect the light from the earliest stars with stunning resolution. We are on the verge of a new era of cosmic archaeology, one that will peer deeper into the darkness than ever before. What other surprises are waiting in the shadows of that forgotten age? The answers will not only complete a chapter in our history books, they may force us to rewrite the laws of physics themselves. These new observatories are not just better telescopes, they are time machines with sharper vision. The Nancy Grace Roman Space Telescope, for instance, will not simply look deeper, it will look wider, conducting a grand cosmic census that will uncover millions of galaxies from the epoch of reionization. Its field of view is 100 times larger than that of the Hubble Space Telescope, allowing it to sweep vast swaths of the sky and find the rarest, most ancient objects that have previously eluded us. It will map the distribution of dark matter in 3 dimensions by observing how its gravity bends the light from countless background galaxies, finally giving us a detailed chart of the invisible cosmic web as it was being built. The Square Kilometer Array, or SKA, takes a completely different approach. This is not a single dish, but a forest of radio antennas spread across 2 continents, working in concert to create a collecting area of over 1 square kilometer. Its primary target is the faint radio whisper of neutral hydrogen from the Dark Ages. The SKA aims to create a 3-dimensional movie of the universe's evolution, showing us the distribution of hydrogen gas as the first stars and galaxies ignited and began to carve their transparent bubbles. It will witness the cosmic dawn in radio waves. The technological leap required for this is staggering. To detect a signal that has been traveling for over 13 billion years and is now incredibly faint, the SK must be built in radio-quiet zones, far from human interference, and will rely on supercomputers capable of processing more data in a single day than the entire global internet traffic. It is like trying to hear the rustle of a single leaf in a hurricane, and it requires engineering on a heroic scale. What specific mysteries will these tools tackle? The Roman telescope will hunt for pristine, metal-free stars in our own galactic halo, the direct descendants of the very first stellar generation. Finding even a handful would be like discovering living dinosaurs, offering an unspoiled look at the chemistry of the infant cosmos. The SKA will test the very timeline of reionization, measuring precisely how quickly the fog lifted and whether it was a smooth process or a chaotic series of clearings. These missions will work in concert, with Roman identifying the early galaxies and SK mapping the gas they are transforming. We are on the cusp of moving from static snapshots to a dynamic film of the universe's childhood. How will this new evidence rewrite our cosmic narrative? It could confirm that dark matter behaves exactly as we think, or it could reveal a flaw in our fundamental model of gravity. It might show that the first stars were even more massive and spectacular than we dreamed, or it could unveil an entirely unexpected pathway for galaxy formation. With sharper lenses focused on the deepest past, we are not just looking for answers to our existing questions, we are preparing to be astonished by questions we have not yet learned to ask. This search for our ultimate origins forces a profound shift in perspective, from the mechanics of cosmic evolution to the very meaning of our place within this grand story. The entire history of human civilization is a single, fleeting breath in the cosmic day. Understanding the universe's forgotten age does more than fill a gap in our textbooks. It redefines our sense of place within an almost unimaginable timeline. We are living in the universe's old age, looking back across billions of years to witness its birth and awkward adolescence. The atoms that form our hands, our planet, and the air we breathe were forged in those first stellar explosions, scattered by the very processes that ended the cosmic dark ages. We are not just observers of this history, we are a physical product of it, a temporary assemblage of ancient stardust that has become conscious of its own origins. This knowledge evokes a profound humility, a feeling captured by the astronomer Carl Sagan when he reflected that we live on a mote of dust suspended in a sunbeam. Our triumphs and tragedies, our art and our wars, all unfold on a stage that was constructed over eons of cosmic evolution, a stage we have inhabited for only a vanishingly brief moment. How does this scale alter our search for meaning? It suggests that meaning is not handed down from the cosmos, but built by us, the universe's way of understanding itself. The quest to find other life takes on a new dimension, framed not as a search for aliens, but as a search for cosmic siblings, other expressions of the same universal processes that led from hydrogen to complexity. We are like a single, sustained note in a grand symphony that has been playing for 13.8 billion years, a note that contributes its unique, fragile beauty to a composition of overwhelming power and duration. This perspective does not diminish us, it connects us. It tells us that we belong to a story far greater than our own, a narrative of transformation from darkness to light, from simplicity to rich complexity. As we prepare to bring this journey to a close, we carry with us this dual sense of insignificance and profound connection, standing at the end of a cosmic lineage that stretches back to the first spark in the void. This journey through the cosmic dark ages reveals a universe not of emptiness, but of immense potential. From the profound silence that followed the Big Bang's fading glow to the first brilliant sparks that ignited the epoch of reionization, this forgotten era was the universe's essential workshop. Here, the invisible hand of dark matter sculpted the cosmic web, providing the scaffolding upon which everything would be built. The first monstrous stars lived short, violent lives, and in their spectacular deaths, they became the universe's first alchemists, seeding the cosmos with the heavy elements that would one day form planets and life. Through relentless mergers and the delicate balance of cosmic feedback, these initial structures grew into the diverse galaxies that now fill our night sky. The final clearing of the primordial hydrogen fog marked the end of this Middle Age, unveiling a transparent, structured cosmos ready for its next act. Every spiral arm, every aging star, and the very atoms that compose us are the direct legacy of this foundational chapter. The mysteries that remain, from the true nature of dark matter to the origins of the first supermassive black holes, are not endpoints but invitations. They are the frontier for the next generation of telescopes and for the curious minds that will interpret their data. This story of transformation from a simple, dark void to a complex, luminous reality speaks to an incredible capacity for change woven into the fabric of existence. Our quest to understand it is a profound way to connect with our cosmic ancestry. We are the universe awakening to contemplate its own origins. If this exploration of cosmic history sparked your curiosity, share your thoughts in the comments below. For more journeys to the edges of space and time, be sure to subscribe. Remember, each time you look up at the stars, you are gazing back into a hidden history of darkness and light, a story of becoming that is still being written.